Hey there, y'all. Today we're going to look at 1.2 on simplifying radicals with variables. So like we looked at in 1.1, we're going to be using our properties of radicals to be able to simplify these expressions. But the ones we're going to look at today are going to include variables with powers on them. And so let's look at a couple examples of these and see how it works. So in example 1, we see the example A, square root of 9x squared. Well, we want to use that product rule to separate this out like we did in section 1. And so we're going to rewrite this as the square root of 9 and the square root of x squared. And then we're able to take the square root of each piece. So the square root of 9 is what? Well, that's 3. But when we deal with the variable, we've got to think about the powers, right? And so this is a square root. We can think about that little tubing there. The square root cancels the square, leaving just x. And so the square root of 9x squared is just 3x. There would be no radicals left. There's no powers left in this case because it's simplified down. It is what it is. Let's look at example B. We have the cube root of 27y to the 6th. And in this example, again, we want to separate it out. And this time we're a cube root, so cube root of 27. And the cube root of y to the 6th. And so the first part, cube root of 27, so what times itself is going to give us 27. Well, that's 3. And then we look at the powers here. We see that our root is 3 and our index, or our power of the y is 6. And so we can rewrite that using our property. We talked about it yesterday. We said that y to the 6 over 3, right? Because remember, the power is going to be the numerator and the index is the denominator. And so we're able to now reduce this fraction. Well, 6 over 3 would be y squared. And so our final answer here is 3y squared. Again, there's no radicals left. It's completely simplified down. And so as you look at these values, think about what is going to factor out, how we can separate into its separate pieces. All right? And so in example 2, we're going to look at some that don't perfectly reduce. We're going to get left with some radicals. So let's take a look at those. So as we discussed in 1.1, there will be expressions that are non-perfect numbers or powers. And so like, for example, taking the square root of 8. Yeah, we can simplify it, but it doesn't come out to just the number like the square root of 4 coming out to 2. And so anything that will simplify is going to come out of the radical and be what it will become. And anything that doesn't simplify will just stay under the radical. And so we're going to look at how that will work here. So let's look at example A. The square root of 12 x cubed. So again, we're going to split that off. Square root of 12, square root of x cubed. So square root of 12, square root of x cubed. Now, we think about that square root of 12. And we're dealing with square roots here, so we want to think about our perfect square numbers. 1, 4, 9, 16, 25, so on. Can any of those divide by 12? Yeah. 4 times 3 is 12. And so the square root of 4 is 2. The square root of 3 does not simplify, so it's going to stay exactly as it is. Now we come over to the variable part. Well, I've got a power of 3, and our index is 2 here. Remember, if there's no index, the index is 2. And so I want to be able to divide this into an equal number of parts, and then anything separate will stay under. And so multiples of 2, 2, 4, 6, 8, 10. Well, there's a 2 here, right? So I can separate this out to x squared times x. Because remember, we were going to add those powers back together. And so the square root of x squared times the square root of x. This part's going to simplify here because the square root will cancel the square, leaving just the x. And this square root of x will stay under the radical. And so at this point, we've got 2 square root of 3 times x square root of x. Well, the parts that are outside, the 2 and the x, we can write that out front. 2x. And the parts that are under the radical, the 3 and the x, we can write that part under one radical, 3x. x. And so this would be our final simplified answer, 2x square root of 3x. Okay? So again, as we break that out, we want to break it out into its separate pieces. We're going to look at a second example here with two variables in it, and also, again, another number that's not going to perfectly simplify. So let's look at that. In example B here, the cube root of 16, x to the 6th, y to the 5th. So again, we want to break it out into each separate piece. We're going to talk about the cube root of 16. We're going to talk about the cube root of x to the 6th. We're going to talk about the cube root of y to the 5th. So cube root of 16, cube root of x to the 6th, cube root of y to the 5th. And we'll talk about each piece individually, and then we'll bring it all back together into one final answer. So we first need to look at how can we split the cube root of 16. Well, we're looking at perfect cubes here, so 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, so that's above 16, so we can stop counting. But 8 is a factor of 16, so we can do the cube root of 8 times the cube root of 2. And like we just said, the cube root of 8 is going to be 2. So we get 2 cube root of 2. We're going to hold on to that piece for a moment. Let's go to the x part. So the cube root of x to the 6th. Well, 6 is a multiple of 3, so we can just rewrite it as x to the 6 over 3. And 6 over 3 is what? That would be 2. So we get x squared. There's no radical part left for the x. We go to the y. And again, we want to think about how this could separate out. Well, 5 is not a multiple of 3, so we're going to have to think about what can separate. So we get y cubed, because 3 is a multiple of itself. And then how many powers are left? Well, we pulled out 3, so there's 2 left. So we're going to get y squared. And then we can split this. So we're going to get the cube root of y cubed times the cube root of y squared. And over here, the cube root and the cube will cancel, leaving just the y. And in the other part, the cube root of y squared is going to just stay what it is. Cube root of y squared. And so we're going to take all these parts. We've got this, this, and this. We're going to write it all back together and then combine the parts that are outside the radicals in front and simplify anything we can. And then anything that's not out of the radical, everything that's staying in the radical, will stay under the radical. And we'll simplify it into one expression. So let's rewrite it together. So 2 cube root of 2 x squared y cube root of y squared. And so the parts that are outside, we've got a 2, an x squared, and a y. We're going to write all three of those to the front. So 2 x squared y. And then the parts that are under radicals, cube root of 2y squared. This would be the completely simplified answer. Again, it looks a little longer than what the original problem is, but it is simplified because we pulled out like terms. Like we talked about in 1.1, like reducing a fraction, the same idea applies here. Okay? We're going to look at example 3 and a couple of problems where, again, we need to remember that fractional powers mean radicals. And so that's what we're going to look at in example 3. So remember that rational exponents are able to be rewritten as radical expressions. We will use this property to simplify expressions like we did in examples 1 and 2. And so in example 3, we have 27x squared raised to the 1/3 power. And so because the numerator is 1, there's no extra power that we're dealing with. But the denominator is 3, so this is going to be a cube root of 27x squared. And so like we did in example 2, we're going to split this up, simplify both pieces as best as we can. And so we're going to have the cube root of 27 times the cube root of x squared. Well, the cube root of 27, so what times itself will give us 27? Well, 3 times 3 is 9. 9 times 3 is 27. So the cube root of 27 is 3. And then the cube root of x squared. Well, in the previous problems, our power was larger than our index, and so we were able to pull something out and maybe leave something behind. But here, the power is smaller than the index. And so there is no simplifying this any further because there's not a whole piece that we're going to be able to factor out. And so we're going to leave this piece, cube root of x squared, and that's just our final answer. Okay? Let's look at one more example, example B here. We have 48x to the 5th, y to the 8th, to the 1/2 power. So again, we're going to write it as a radical, and then we'll do what we did in example 2 and separate it out. So we're going to get the square root of 48, x to the 5th, y to the 8th. And again, now we're going to break it out into the 3 pieces. So square root of 48, square root of x to the 5th, square root of y to the 8th. So the square root of 48, well, can I take the square root of 48 and get a perfect number? No, because square root of 49 is 7, so square root of 48 doesn't work. But is there something I can divide 48 by that is a perfect square? Well, okay, so 1, 4, it does divide by 4, but let's see if there's something else. 9 doesn't work. 16. 48 divided by 16 is 3. So we can separate this out to square root of 16 and square root of 3. And this is a great point for me to stop and just talk about when we have multiple perfect square factors that are involved, like 48 can both divide by 4 and divide by 16, we always want to take the largest perfect square factor, because otherwise we'd have to reduce it again. Kind of like reducing, let's say, 24 over 36, right? Well, we could divide both those by 2, but that's only going to give us 12 over 18. And we could reduce it again, right? We always want to reduce by the largest factor we can. And so 16 is that number here. Square root of 16 is 4, square root of 3. We look at the x part. Again, we're doing a square root. If you need to put that 2 there, that's okay to remind yourself what power we're dealing with. So we're looking at multiples of 2. So 2, 4. We can't go to 6 because we don't have enough. But we can go 2, square root, x to the 4th times x, because 4x's and 1x give us 5x, right? So we can break that up. Square root of x to the 4th, square root of x. So this is going to reduce, right? So x to the 4th over 2. And so 4 divided by 2 is 2. And then we do our y's. Well, again, we're doing a square root. So y to the 8th over 2, right? So 8 over 2 reduces to 4. So this is y to the 4th. And so we're able to combine our pieces together. Again, anything outside the radical is going to go to the front and be written together. Anything that stayed in the radical will be under one radical, just again multiplied together. And so let's see those pieces. We've got a 4, we've got an x squared, and a y to the 4th. So we're going to have 4x squared y to the 4th. And the pieces under the radical, we've got the square root of 3x. So this would be our simplified answer here. All right, so that is it for this lesson today. Again, big thing to remember. Use the powers to your advantage. Think about what perfect roots will be able to come out. Perfect squares, perfect cubes, if we have a 4th power, perfect force. So again, think about those values. And if you got any questions, remember to leave them in the lesson check, and we'll talk about this next time.